Welcome back to the Explainer Coder Army. Today we're embarking on a super fascinating deep dive into a question that honestly comes up all the time in technical interviews, yet so many developers only kinda understand it on the surface. We're gonna uncover exactly how Java stores negative and floating point numbers in memory. Because, well, here's the thing, we all know computers only understand binary, right? Just zeros and ones. They literally do not understand decimals, and they for sure don't have a concept of a minus sign. So what on earth is the computer actually doing behind the scenes when you declare a variable? Let's unravel the mystery of what the hardware actually understands.
Okay, let's kick things off with a massive illusion that Java's hiding right under our noses. Imagine you write a really simple piece of code. You set a float variable to 8.125. You print it, and it outputs 8.125. Perfect, right? Now you set a float to 0.7. You print it, and it says 0.7. You're probably thinking, great, it's storing exactly what I typed. But Java is actually pulling a fast one on you. It's rounding the number just to make it look pretty for you. If we use a formatting function to ask Java to print that exact same 0.7 float out to 20 decimal places, it completely exposes the trick. Instead of 0.7 followed by a bunch of zeros, Java spits out 0.69999880701044492. It turns out 0.7 isn't perfectly stored at all. It's a total illusion. And to solve this mystery, we first need to understand how the most basic building blocks are stored.
All right, let's jump right into our first topic, storing negative numbers.
Think about this for a second. If I ask you to store a positive 42 in an 8-bit byte, it's pretty straightforward. You just translate 42 into its binary equivalent. But I want you to ask yourself, how do you store a minus sign when you don't have a minus key? In a strictly binary world made entirely of zeros and ones, how do we tell the computer that our number is, say, negative 42?
The answer actually lies in this brilliantly elegant mathematical trick called 2's complement, and it works in 3 really simple steps. First, you completely ignore the negative sign. Just pretend it's not there. You take the positive version of the number, so positive 42, and find its standard binary representation. For a standard byte, that's 00101010. Step 2, we create what's called the first complement. All you do is invert every single bit. Every 0 becomes a 1, and every 1 becomes a 0. So our binary flips to 11010101. Finally, step 3, you take that flip sequence and you simply add a binary 1 to it. After carrying over the addition, you end up with your second complement, which is 11010110. And boom, that is exactly how negative 42 is stored in your computer's memory.
And this is where it gets cool, because it illustrates exactly how the computer knows it's looking at a negative number in the first place. It is all about the most significant bit, or MSB. If you look at any 8-bit sequence, the MSB is that leftmost bit. It carries the most significance, or mathematical weight. If you change it, the total value of the number changes drastically. Conversely, the rightmost bit is the least significant bit, or LSB. Java has a super strict rule. When reading these bits, if the MSB is a 1, the computer instantly knows it's dealing with a negative number. If the MSB is a 0, it's positive. Because of the 2's complement method we just did, every single valid negative number naturally ends up with a 1 in that leftmost position.
Now this leads us to a really fascinating mathematical quirk, the negative 0 problem.
You might be wondering, why do we even need that final add 1 step? Why not just use the first complement, flip the bits, and call it a day? Well, let's look at the number 0. In binary, a byte of 0 is simply 8 zeros, 000000000. Now, what if someone artificially tried to store a negative 0? We know mathematically negative 0 doesn't exist, right? It's invalid. But if we applied the first complement rule to 0, we'd flip all those zeros into ones. We would end up storing 1111111. Because the MSB is a 1, the computer would absolutely read this as a negative number. We would have accidentally created a mathematically flawed negative 0 inside our system.
So the crucial takeaway here is how 2's complement absolutely neutralizes this flaw. Let's apply that final step to our fake negative 0. Take 11, 11, 11, 11, and add 1. What actually happens? Well, 1 plus 1 is 0, carry the 1. That carries all the way down the line. It literally forces an overflow. The result pushes out a brand new 9th bit. But remember, a byte can only hold 8 bits, so the processor just drops that 9th bit right off the edge. And what are we left with in our 8-bit container? Exactly 8 clean zeros, 00000. By forcing that overflow, 2's complement ensures that 0 remains absolutely unique with no negative counterpart. It is just an incredibly elegant safeguard.
Okay, shifting gears to our next section, the anatomy of a float.
Floating point numbers are a whole different beast compared to integers. They follow a highly specific IEEE 754 standard, taking up exactly 32 bits of memory. And these 32 bits are sliced up into 3 very distinct compartments. The very first bit is the sign bit. Again, 0 for positive, 1 for negative. The next 8 bits are reserved for the exponent, and the remaining 23 bits, those are called the mantissa. When Java converts a decimal, it basically calculates a binary fraction and normalizes it into a specific scientific format. The base data of that fraction gets stuffed into the 23-bit mantissa, and the power it's raised to goes right into the 8-bit exponent.
But within that exponent calculation lies a magic number. And trust me, this is a highly requested topic in technical interviews. That number is 127.
This magic number is known as the bias. Now, what's really interesting is why we even use a bias. Sometimes when you convert really tiny decimals, your exponent becomes a negative number. But hardware processors work significantly faster when they don't have to deal with calculating negative signs in the exponent field. So the IEEE standard dictates that we take a predetermined bias, which is 127 for a 32-bit float, and we simply add it to our actual exponent before we store it. By shifting the entire scale up by 127, Java ensures the processor only ever stores and calculates using positive, unsigned binary numbers in that 8-bit exponent slot. It's a pure performance optimization trick, and it's brilliant.
So, let's bring it all back home. Section 4. Why decimals lose precision.
Remember our 0.7 float from earlier? The one that somehow magically transformed into 0.699999? Here's exactly what happens under the hood. To convert a decimal fraction into binary, Java repeatedly multiplies the decimal by 2 and pulls off the whole number. Let's trace 0.7. Multiply by 2, you get 1.4. Keep the 1, carry the 0.4. We take that carried 0.4, multiply by 2, get 0.8. Carry the 0.8. Multiply by 2, get 1.6. Keep the 1, carry the 0.6. Multiply by 2, get 1.2. Keep the 1, carry the 0.2. Multiply by 2, get 0.4. Wait a second, we just hit 0.4 again. The cycle just restarted. We will endlessly generate 0.4, 0.8, 0.6, 0.2 forever. This calculation literally creates an infinitely repeating binary sequence of 0110.
And here is the fatal flaw in the system. Java tries to store this infinitely repeating binary fraction, but it hits a hard brick wall, the mantissa. Remember, the mantissa can only hold exactly 23 bits of data, literally no more. So what does Java do with an infinite loop? It forcibly chops it off the second it hits that 23rd bit. The rest of the infinite data is just thrown right into the void. Because the data was physically truncated, when Java pulls it back out of memory later and tries to convert it back to a decimal, it just doesn't have the full picture anymore. It calculates what's left, and you get that 0.6999 error. The precision is permanently lost the exact second it hits the 23-bit ceiling.
Which brings us to our final section, double precision and beyond.
So a really common workaround you'll see is developers abandoning float and using the double data type instead. A double upgrades the architecture to 64 bits. The exponent gets 11 bits, which changes our bias to 1023, by the way. But crucially, the mantissa gets a massive upgrade to 52 bits. This gives you way more runway to store binary fractions. You will absolutely get much higher accuracy than a float. But does it actually solve our infinite loop problem? No way! Infinity is still larger than 52 bits. A double will still eventually chop off the repeating sequence, meaning it too will ultimately fail to give you absolute, perfect exactness for numbers like 0.7. It's really just a much more accurate estimation.
Which leaves us with a pretty massive cliffhanger today. If both float and double are fundamentally flawed by binary truncation, how on earth do banks, financial institutions, and rocket scientists do precise decimal math in Java? Well, Java actually has a foolproof, non-primitive data type built exactly for this purpose, called big decimal. But how big decimal manages to perfectly bypass these hardware limitations is a massive topic all on its own, and we'll be doing a complete deep dive into that next time. Until then, think about this. If the very foundations of computer memory are built on rounding errors and infinite loops chopped in half, what other silent illusions are running inside your codebase right now?